All right. Well, we're going to get going and I'll see if anyone else is going to join us. So today I'm going to give an introduction to secondary storage. So for some of you on the call, you'll be from Professor Pasricha's classes, either master's or PhD students. And then for some of you, you'll be the interns for the 2025 summer. So this would be a kind of basic overview of what secondary storage is, how it works, what hard drives are versus SSDs, and basically some details behind the bus architecture and the future of secondary storage. So some quick background for those who haven't already met me. I'm Eric Hoffander. I'm a principal engineer in the hardware division. I worked on control systems and SoCs for 15 years. I do a lot of the host drive communication as well as inner SoC communication, and I'm a current PhD student in embedded computing. So first, I want to give a little bit of background on what secondary storage is and how it differs from main memory. So primary storage is basically any of the memory within the computer that is byte level accessible. So when people say like computer memory, generally what they're talking about is things like DRAM. But as we've seen, it's kind of a large architecture going from the very top to the very bottom. Everything needs to be accessible from the memory bus or is internal to the CPU. Generally, when we're working primary storage, we're very, very IO latency driven. So we have billions and billions of IOs. However, primary storage, external to caches, is still orders of magnitude, hundreds to thousands of times slower than the actual registers themselves. Secondary storage is what I'll be talking about today. So this is what people think of when they think of like, I have 1 TB of storage on my computer, or when they're storing something like a movie or something like that. That's going to secondary storage. Secondary storage is everything that's block accessible. So in primary storage, if I have some pointer, like in C code, hex, some series of 8 different hex numbers, that's a pointer. Secondary storage doesn't work like that. What secondary storage is blocks. So each of the blocks is either 512 or 496 bytes in size, and there are no actions that I can perform that are smaller than a single block. Now, secondary storage may not be on the bus at all. So for most of our present computers, they are all on a bus. But for most of the history of primary storage, they've not been. Secondary storage is always persistent. So no one's going to want volatile secondary storage. You don't need a hard drive that can't remember what it's done. The whole point is it's persistent on power loss. And the big thing is it needs to be cheap. So secondary storage is thousands and thousands of times or millions of times cheaper than primary storage. The big problem now is that it's slow. So tape is something that's used for offline storage and still exists. So we have 2 different tape standards that still exist out in the world. In tape, really, there's not a concept of IO per second. Basically, you stream a file somewhere, and those files are very, very large. Generally, when you're working with tape, you do an entire tape read or write in one action. SAS, SATA, we have hundreds of IOs per second. And then NVMe is directly attached to the bus. So this is the future of storage. So here we can have thousands to hundreds of thousands to possibly millions of IOs per second. And the important part is it's attached to the bus. So generally, secondary storage is abstracted from the CPU. What that means is the operating system actually does the requests. So if I'm a CPU and I'm in a program, I can basically access any pointer I want. Now, obviously, if I'm outside of ring 0 controls, accessing some memory will cause a fault, but basically the entire bus is available. That concept doesn't really work for secondary storage. Secondary storage, generally, you make a request to a device, and that device may or may not answer your request. All of the data itself is going to be streamed via DMA. Now, in the past, this would work differently via PIO, but we'll talk about that later. So The next concept is kind of how slow secondary storage is. And this is kind of hard to understand. But here's kind of our tree of storage. Now, in this tree, at the very, very top, obviously, we have our CPU registers. Now, registers are the actual things you can perform data operations on. Now, I say less than 1K here. Obviously, if you're gone through the classes, you know that we can have a ton of different streams. So we'll have a ton of different states. You have your entire pipeline. But we'll not really think about that right now. We're just going to look at one solitary pipeline. From there, we have our caches. So here, our size is increased probably by a factor of 100, but we're much, much slower. On a real processor, it's going to be, 100 times slower, again, because we're not truly pipelined. And generally, we do not do real actions in the cache. And in each size, as we go up, generally we go up it by an order of magnitude, and we slow down by an order of magnitude. In our first four areas, all of this is SRAM, because SRAM is fast and it doesn't need to be modified. It's not dynamic. We don't need to refresh it. Below that, we have our line-based storage. So this is what people think of in terms of the main storage on their computer. So DRAM, generally by chip, the max size is about 8 gigabytes. However, what you do when people think of a DRAM chip is they think of like an entire assembly. And that will have many DRAM chips put together. And there you can have things like banking, streaming, all the things you guys are used to. So on the side of this, I have NOR Flash. Now, NOR Flash is byte-based, so you can access it like I can primary memory. However, it's persistent. NOR Flash is very strange, but it can actually, you can directly execute from NOR Flash. And this is really important because generally a CPU will boot without anything active except for a small area of NOR Flash. So the very, very beginning, on your reset vector, this is where you're executing from. So below here is what we're going to be talking about today, which is secondary storage. And again, instead of line-based access, where I'm accessing an entire line, so 64 bits times 4 for 32 bytes, we're going to be doing it by page. So rather than 32 bytes, we're going to be accessing 4 kilobytes at a time. And there's no operation that I can do to modify a single byte within that. And here again, we're going to have an increase in size with a decrease in speed. So on the top, there used to be SLC flash, but in general, almost no one uses the SLC anymore. Generally, we'll be using MLC or TLC for our performance flash. And then for our low cost flash, we'll be using something called QLC flash. Below that, we'll have hard drives. So you'll see here the hard drive is much larger, and that's simply because the physical size is larger. Generally, when people think of like, oh, this flash drive is 8 terabytes, what they really means is it has a number of chips in it that all add up to 8 terabytes. The NAND chips themselves are generally right now topping out at about 512 gigabytes. Again, when you're dealing with memory in chips, everything is generally going to be in gigabits, not gigabytes. So be very careful, because if you're not careful, you'll assume things are much, much larger than they actually are. Below hard drives, again, we'll have tape, largest of which is about 50 terabytes. I have it kind of outside of secondary storage. In the modern era, basically no one directly talks to tape drives. Almost everything is done by a tape library. So basically all of tape would be considered offline storage. So offline storage is generally, you're not going to be accessing it on any type of bus. You'll be talking to it via Ethernet or fiber, something that's not physically attached to my computer. And finally, we have offline storage. Now, the joke is, of course, that cloud storage doesn't exist. There's simply other people's computers. And that's, again, what I'll kind of be emphasizing here. Generally, everything that's offline is going to be very cold. And that means that it's going to be read very seldom and almost never written. Why this whole stack exists, again, is just because how much faster CPUs are than anything else. A single execution will waste so much time. My favorite story on all this stuff is, imagine you're in a library and you're the CPU. And you can, in your head, you can think of 2 or 3 numbers at a time without writing them down. So to do actual work, you take a sheet of paper with you, and that paper is your L1 cache. And you can probably write down 100 to 1,000 things more than you can actually remember accurately. It's slower than you can think, but maybe by only a factor of 2 or 3. So you need more room. So you grab a notebook. You have, 100 sheets on it. Now it's going to take maybe 10 times longer to look through those sheets, but you have 10 times the space. That's your L2 cache. And now you have a textbook. And this is your last level cache. So now you're much slower than your notebook, and it might take you, a minute to find it with your textbook. But you're in a library, and the library has thousands and thousands of books. However, now it's going to take you 10 minutes or an hour to find something in this library. And that library itself is your DRAM. Now, how does this compare to secondary memory? Well, put a hat on, because we're going to build a sailing ship from the 17th century, launch it, and then sail it to Europe. Once it's there, obviously, Europe's very big. It has billions of books. And the ship has a very big volume, so it can carry lots of books. But it's going to take years for you to get your data back. And that's basically to scale in terms of what a CPU is dealing with in comparison to the different secondary storage speeds. So the hard drive, in a single I/O time, during that time, my CPU on the laptop sitting next to me can access about 30 trillion floating point operations. So if it's so slow, why does spinning Rust still exist? So fundamentally, the answer is money, right? So even though Flash has gotten much cheaper, the reason it has gotten cheaper is not necessarily going to stay around forever. And that has been the move from SLC to MLC to TLC to QLC. What we're doing now with Flash is we stack. So when you hear 3D Flash, what you're doing is you basically take a silicon wafer, you build one level of Flash on it, and then you're going to stack it. So to create the largest QLC flashes, right now we have 214 layers. So 214 chips stacked on top of each other to get us that 8 gigabyte storage. The also issue, of course, is, it's write limited as we move to QLC. But we have huge benefits, obviously, in NAND. No moving parts, there's no physical locality, and it's not vibration sensitive. Fragmentation here, in other words, if I have data spread out all over the chip, that's a very good thing. On the hard drive, we have moving parts. It's very sensitive to vibration. However, it's much, much cheaper. So generally about 10 times cheaper than Flash, but fragmentation is now very, very bad. Over here, you see the cost flow, and this is in log scale on the y-axis. You can see here, the hard drive price is going down very, very quickly. But then around 2004, we start to have flash memory become competitive. And around mid 2010s, we have NVMe flash starting to take over. So in general, over my career, hard drives have fundamentally changed. We used to be, when I started, an IOPS box, basically where we'd send lots of IO requests and service lots of IO requests. That's no longer the case. Now we are much closer to what tape was. We are sequential operations, and on top of us, we have fast flash. So this picture is basically why hard drives exist. So this is a Google data center, and what you're seeing here are racks. So the racks are a standard size, and within each of these racks, we are going to stuff as much data as we possibly can. And right now, you can stuff more space in terms of flash because they're smaller. However, you can't cost competitively sell that data on the market. Generally, when I have a customer, like, some girl who's uploading a lot of stuff to Instagram, or someone who's uploading a bunch of videos to YouTube or something like that, that data is extremely cold. Now, we might think, oh, I'm super popular, everyone looks at my photos. They're going to look at them once, and then no one might ever look at them again for many years. That data is incredibly cold. So it makes sense as soon as the data temperature decreases to move it to cheaper and cheaper storage. So while, if I post the new television show onto Netflix, that day is going to be very hot. Millions of people are going to be looking at it. But if I'm looking at some recorded lecture from someone, you know, 5 years on, I might be the first person to access that data in years. And there just doesn't make sense to store it on something that can service thousands of operations a second. So again, just like I move things from the L1 cache to the L2 cache as they get old, I'm going to do the same principle with my storage. Again, this is just a closer look. So this is a 4U rack, which is a standard size. Within this, people are basically going to stuff as many hard drives as they can. Basically a hard drive torture chamber of 80 drives all stacked next to each other with a hurricane force winds pushing across them. And there'll just be rooms and rooms and rooms of these. So on NAND flash, these are the difference for what we're calling SLC, MLC, TLC, and QLC. And this again is just how many bits we're storing. So what we want is digital data, but what we're storing is so to speak, an analog number of electrons within the gate of a NAND transistor. If we're doing QLC, that means we have to have much more sensitivity. We have to be able to distinguish 16 states accurately from each other. So that means the difference here is much, much, much smaller than the difference here and here. You're getting further and further away from that binary. So in general, in NAND, write is very expensive and read is almost free. Reading doesn't cost us much. How we address the issues is basically we put lots of NAND flash chips together. And as files are hot, so they're written often, we can't write them to the same place. On a QLC NAND chip, we might only get 10 to 50 writes per block before the drive is out of writes. That's very, very small. And we can't sell that. So what we do is we do write-where leveling. So each write is written to a unique place, and all the data is moved around. Problems that will cause is as the device fills up, we have a problem called write amplification. So we write somewhere, we move the data that was there to somewhere else, then we have to move that data. So a single write here causes 4 additional writes. So it's a write amplification of 5. That problem gets worse and worse and worse as our device fills up. So what we do is what's called over-provisioning. So we sell 1 terabyte of storage, but we actually build 1.4 terabytes. That obviously costs money. So you can only do that on a premium product. So generally, as your flash gets cheaper, your over-provisioning gets less and less. Now, the thing I want to emphasize here again is files don't exist. So if I plug in a hard drive, it has no concept of, oh, this folder's on here, this thing's on there. Files do not exist. Things that exist are these things called logical block addresses that all contain 4 kilobytes of data. So what people do is they will, at a special LBA at the beginning, they'll create what's called a file allocation table. Now this has a unique format, and that's what you hear when you hear like FAT32 or NTFS. That is this file allocation table. It's a special way to associate file names with LBA ranges. Again, the device doesn't see file requests. What it sees is LBA reads and writes. So secondary storage, we have kind of 3 main ways to talk to a drive. NVMe, which is the non-volatile memory express. So this is the PCIe direct storage. We have SAS, serial attached SCSI, and SATA, serial attached ATA. So the important part of NVMe is that it's bound to the PCIe bus. So what that means is it is directly attached to the same bus that can see primary memory. So while this is a serial link of n number of channels, up to 16 channels, it can directly write into memory without ever passing through a bus adapter or through the CPU. It's also in NVMe, we have the concept of a target, not the concept of an endpoint, not the concept of a target. And endpoints can actually write across each other. So if I have two flash devices, I can actually have them write to each other directly and never touch main memory at all, which is really great because it saves me on DRAM, it saves me on CPU time. All those things are great. SAS and SATA are different. So they actually have a very, very long legacy. SAS, serial attached SCSI, comes all the way back from the 1970s, a different protocol called SCSI. And this protocol is based on the concept of an initiator and a target. So my initiator in the past was my main computer, and it said, give me LBA 1000. It sent that to a target. That target would receive the data, and they would send back a response. Targets do not talk to other targets. Initiators don't talk to other initiators. That has been updated over and over and over again. It's millions of times faster than it was in the 70s, but fundamentally, the protocol is pretty much the same. As we move forward in computing, this is basically going away as we move closer and closer to everything being on a common bus. So, getting to the heart of it, what is a disk drive? So disk drives are a magnetic media called the disk. And on this disk, we have hundreds of thousands of tracks. And each track will store the data we want in the changing magnetic field. There's a head, which here you see on a ramp, connected to a suspension, connected to a voice coil. Now this head has a physical wing on it, and it's going to fly above the disk surface based on air pressure. On the end of that flyer, called the slider, there is a head. And this head will be moved up and down from the slider towards the disk surface. And this head can be moved within angstroms of the disk during writes. And again, a modern drive is going to be up to 40 terabytes in size, so 10 to the 10th sectors on this piece of disk, and we have to be able to find each of them uniquely within a few milliseconds. So hard drives are basically impossible. They're going to find tracks the width of a DNA strand in 2,000ths of a second, then read magnetic data in 16 microseconds at a rate of 2.4 billion bits per second. And we're going to do this while flying the reader at a height of 8 hydrogen atoms away from the disk surface. They contain a gigasample oscilloscope, 4 different atomic precision actuators, 10 disks, 20 surfaces, and are going to store hundreds of trillions of bits. It's the most precise, fastest 3-axis robot on Earth. And we're going to sell it for $300. So the first problem, of course, is we're going to need to control our radial position. So this is the main suspension arm, and it's going to be able to have to move across the entire disk surface. Now, if you guys have taken any controls, you're going to see this is a problem because this suspension is large. I can physically see it, right? So you don't need to look at me anymore. We're going to start looking at hard drives. Okay, you can see that suspension arm. It's physically large in size. I can guarantee you that physically large thing is just by me breathing on it is going to move more than 1,000 atoms across. It's never going to be able to have that precision control we're talking about here. So what we're going to do is we're going to stack actuators on top of each other. So here you see an image of a modern actuator. So here's the main actuator. The VCM is so large, I've not pictured it here. You'll next have these milli actuators. So these are PZT crystals. So as I apply a voltage to them, they are going to change in size. Now that's going to give me faster, much faster control because again, the inertia in this arm out here is smaller. And at the very tip, I'm going to have a much smaller PZT. So again, a piezoelectric actuator. And it's going to have even higher frequency. So just like with we were talking about memory, we're going to decrease our physical motion, so kind of like decreasing our memory size, but increase our bandwidth. So we have very high bandwidth, but very small distance, medium frequency, medium distance, low frequency, huge distance. So the disk itself is just like a mirror. You can't see anything on it. There's nothing written there. So the disk is not patterned. What we're going to do is we're going to use vacuum depositioning to place rust, basically, on top of the disk surface and then coat it with some interesting things. On top of this, we have to write all of the address markers ourselves. There's nothing there telling us where we are until we write it there. So the hard drive, we say, builds itself. So what you see here is basically the thing that we use to feed back into the system. You know, here is kind of an image of the physical magnetic domains that are written down onto the disk. So within this would be address marks to show us where we are, you know, basically a little signpost saying you are here. And we're not going to get that often because we can't sell it to customers. This is not the physical data they want. This is the data that we have to put there just so that we know where we are. This data is then written to the disk at different locations, and then we can use that to feed back into our own position. Now, physically, as we move across the disk, we have two different latencies we need to think about. So here is basically a plot of an old drive showing how long it takes to move the head somewhere. So we have two different latencies to worry about. The first latency is rotation. So the disk, as it's spinning, takes 8.3 milliseconds to rotate. So if I want something on the other, right behind my head, the worst possible time is 8.3 milliseconds. The seek latency is going to depend on how fast we can move the actuator. So there we're not as dependent on this rotation time, we're dependent on the seek time. So as we get an LBA that's far away, it's going to take longer and longer to get there. So this pattern here is the worst possible pattern. So there's no queuing, we're just randomly picking places. What does that look like? So moving the head takes us physical time. So if you watch here, we're going to go through the load procedure. We spin up the disk. We're going to send the head out onto the disk. You can see that it can move quite quickly. Again, compared to a CPU, it's slower than anything you can possibly imagine. However, to the human eye, it's basically instantaneous. But that physical seek time is what's going to dominate us as we move far locations. So the whole point is, if our data is sequentially together and we don't need to seek, that is the ideal case. So here, as you just saw there in my camera, that is a perfectly random motion. So I choose 1,000 random locations. That head cannot do it any faster than we can pump energy into that VCM. Now, this is actually quite a old hard drive because modern hard drives, I can't put clear covers on. And in fact, they don't even have air inside them. They have helium. But we're going to do this as a demo. Fundamentally, the tri-actuator, you guys couldn't see anyways without a microscope. So what we want to do is we want to pick a better path. So in secondary storage, write latency basically doesn't matter. So write latency we can always fix because we don't necessarily care where it goes, just that it's remembered. So we can just add on more DRAM, write it to somewhere else. Writes we can move around. We can hide it from the CPU. Reads we can't hide. Hard drives are so large that you can't cache anything on reads. So again, if I choose a random location, the chance that it is within the cache, if I dedicated my entire DRAM cache to it, is 0.0005%. So it's completely useless to try and cache random reads. So what you do is what's called prefetch, which I'm not going to get into. So what we do instead is we're going to optimize the read path. So instead of only having one active read to us, we're going to have an arbitrary number of reads. And we're going to do a traveling salesman problem in 2 different dimensions at the same time to get them. So what we do basically is we just increase the queue depth until we can get a more optimized path. So that's what you're seeing here. So as we increase the queue, we're going to force all of these reads writes to go close to the left-hand side. So the LBA distance probability is that all of the seeks are going to be very, very small. Not only that, the rotational latency is going to be minimized as well. So this traveling salesman problem obviously has to be done very, very, very quickly, kind of impossibly quickly. So we can only track up to about 128 paths. On NVMe, that depth can be increased to 64K. That's the thing I'll get into in the future of storage, but fundamentally, that's not really how hard drives are used. Hard drives, people don't care anymore about I/O speeds. What they want is sequential speeds. They don't want any seek times at all. What they'll do is basically just write larger and larger files. So then how are we going to control the fly height? So the fly height is controlled on a atomic scale. And to do that, we are going to actually do it with thermal expansion. So as metal heats or cools, it physically expands and contracts. So at the end of the head, we have physical heaters that will deform in size that are incredibly tightly controlled. So they're built in the same way a CPU is built in terms of lithography. So that will control at a fine position the head. So the slider is this wing I'm talking about. It's a thing that actually flies based on air. The head does not fly. It is held by the slider, and it's going to move towards the disk surface. And that's where we're going to control its fine position above the disk surface on the level of atoms. Now, at the very tip of the head, we have the writer and the reader. So the writer and the reader are going to change the digital data that we were talking about in terms of the sector into analog waveforms that are sent into the writer and reader and sent into the disk. So basically, we'll pass a magnetic flux from what's called a monopole write element. Now, obviously, monopoles don't exist. But what that actually means is that one side of the magnet has a much, much stronger flux than the other. So let's say your south pole is very physically large, and your north pole is very, very, very small. And what that means is that the flux at your north pole is orders of magnitude stronger than the flux at your south pole. And what the disk surface cares about is the flux passing through the surface, not the overall magnetic polarity. So prior to my career, there was a concept called planar magnetic recording, where the flux was actually not up and down as you see here, but kind of left-right, like a cassette tape is. And maybe you guys are too young to know what cassette tapes are these days, but that was like the old way of recording music onto magnetic tape. That was planar magnetic recording. So the reader itself is not a magnet at all. It is just a resistor. And this resistor has the unique property where its resistance will change based on the amount of magnetic flux passing through the resistor. So we're seeing down here. So this is the change in resistance as you increase the magnetic flux. So what we're detecting is, in fact, not the polarity. We don't know what the polarity is. We're detecting only the flux passing through the disk surface. And that flux is going to be based on transitions between polarities. And that's what we're actually going to read back. So again, this is a view basically of about 30 nanoseconds of the data that's coming off the disk surface. And that's basically going to be found by this changing reader. So now we have to lay out the data. So this is basically a cartoon view of what the disk surface looks like. Now there's these things that are a geometric sector, which we call wedges. And within these wedges, there are actual data sectors. And a data sector will contain 4 kilobytes of data. And these geometric sectors will contain an address mark. So as we move around the disk surface, we always see the same number of address marks, but we will see a different number of data sectors. And the reason for that is, again, we have constant angular velocity, but a changing linear velocity. So that means at the OD, we can read and write faster than we can at the ID. It also means that because our writer is physically bigger than our reader is just a little resistor, it means we could lay out our tracks in an interesting way. And that's called SMR. So this is something that came out just about when I started. And that is basically where we're going to write and then overlap our writes, like the shingles on your house. And that's why you can increase your areal density to greater than that allowed by the size of your writer. Fundamentally, what you need is you need track separation. So here's a digital view, basically showing where you can capture data. The red is good, and the blue is bad. So again, that's what you need. You need this physical location to have extent, because even with perfect control, the hard drive is always in motion. So let's talk a little bit about the future. Of course, increasing ADC. If you look at Seagate right now in the news, they'll only be talking about this stuff. And that is that the magnetic domains can only exist within a crystal. So it doesn't make sense to say I'm magnetizing an amorphous material. You can only magnetize a single crystal region. The problem is, as we move our crystals smaller and smaller and smaller, the amount of magnetic flux I need to magnetize them increases so quickly that you begin to get what's called sideband erasure. So the crystals around you start to be impacted by the amount of flux because you can't build your writer any smaller. So what we're doing now is what's called HAMR. So we take a laser to heat up a near field transducer. This near field transducer is quantumly coupled to the disk surface. So it can transfer heat via basically quantum coupling between the electrons in the NFT and the electrons in the disk surface. That heats up the disk surface. Now, if you guys have taken the intro to QM or like Jackson's Classical, you know about like Curie temperatures. So as I increase the metal's and internal electron energy, the amount of energy I need to change the magnetic polarity decreases. So this magnetic spot size that we can get through this quantum coupling is extremely small. So small that we have a single heated crystal that's incredibly small, and our writer can be larger still, but still only write the specific region that is hot. So we write just the hot crystals, and the cold crystals nearby are not written to. So this allows you to have very, very, very small crystals at very, very small track spacings and very high data densities.